All right, we're going to continue to use the Galois group that we found. Oops. And I'm going to observe something that we saw. The fixed field of H, which was the subgroup of the Galois group generated by this R, and was Q adjoined gamma delta, and the fixed field of G, the whole group itself, was Q. Okay, so let's suppose for a moment, suppose we don't know alpha and beta explicitly. We do know G as a permutation of the roots as before, and we do know that information about the fixed field. So H is as before, and we know that when we take the fixed field of H is, I'm going to write it as Q adjoined gamma delta, which is this Q adjoined root 5 that we've been dealing with. All right, let's observe that alpha plus beta and alpha beta are both fixed by this element R, which generates H. Because what does R do? R interchanges alpha and beta. If I interchange alpha plus beta, I again get alpha plus beta. And if we do that to alpha times beta, we again get alpha times beta. All right, so this tells us then that alpha plus beta and alpha beta, these products, are actually in the fixed field of H because they're fixed by R. That's what it means to be fixed, is you're in this guy. Okay, and we also know that if I look at t minus alpha, t minus beta, if you multiply that out, what you get is that polynomial. And that is a polynomial over the fixed field of H, right? Because the coefficients are in Q adjoined gamma delta. So it's a polynomial there. Okay, so what we can do here is we can use the quadratic formula to express alpha and beta as radical expressions of elements in the field that we're working with, which is Q adjoined gamma and delta. Now, in fact, we know already what alpha and beta are, so we don't need gamma and delta to do this. We just need Q. But if we didn't know what alpha and beta were, we would be writing alpha is some radical expression in gamma and delta, and beta is also some radical expression. Radical expression means exactly that. It means an expression with a radical in it. So, so we could write alpha and beta in terms of radicals of gamma and delta. But then we can repeat. And notice that gamma plus delta and gamma delta are fixed actually by all of G. In fact, same is true for alpha plus beta and alpha beta, but we didn't know that a priori. So gamma plus delta and gamma delta are fixed by all of G. So gamma plus delta and gamma delta, are actually in the fixed field of G. And the fixed field of all of the elements of G was just Q. The rationals were the only guys that are fixed. So we can repeat with this guy to express gamma and delta as radical expressions of elements of Q. And since alpha and beta are radical expressions involving radical expressions, they are also sort of expressible in radicals over Q. Okay. So we've just shown, we knew this already, but we've just shown that the roots of our original polynomial are solvable by radicals, by radical expressions. And this is a shadow of how we're going to ask the following question or answer the following question: what polynomials can we find formulas for the roots for? And it turns out, in general, it stops at degree 4, after degree 4. So polynomials of degree 5 and larger don't have radical expressions for the roots. But there's some intimate connection with group theory here that we're going to unravel in this chapter. Oops. But this example sort of gives you an idea of how the group theory comes in, and how the tower of fields comes in, right? Because we have Q, inside of Q we join root 5, inside of Q we join I root 5, and it's all just sort of starting to finally come together.